learn at the moon to enable human missions to Mars. Now, when STMD, or Space Technology Mission Directorate, selects a technology project to come into the Technology Demonstration Missions Program, it has usually been matured in a laboratory setting. It's at least that mature. And then as a full-fledged TDM project, we further mature it into either a ground demonstration test in a space-like environment or a relevant environment, we call it, or we will further mature it into a full-scale flight demonstration. And those, of course, the pinnacle of what we'll see tomorrow during the launch. And so it's impossible to really explain or convey just how NASA's latest innovations will make their way into your everyday life. But we know that the more NASA is tasked with solving difficult challenges, the more we'll need to invent solutions to new problems. And whether we're developing a spacecraft that will navigate on its own, or developing the technologies to, again, land humans on the moon in 2024, America's investment in space technology will continue to improve life on Earth.
Thank you, Tanya. Does anyone have any questions? Okay, well, all right, we're going to hear some more about those technology demonstrations. So it was the invention of a precision timepiece that allowed mariners to usher in the age of discovery. Once they could accurately find their longitude, it revolutionized navigation. So having conquered the oceans, NASA needs to now navigate through deep space. So for more on the Deep Space Atomic Clock, let's welcome two interplanetary investigators from Jet Propulsion Laboratory. Please welcome Todd Ely and Jill Swibbert.
Hi, I'm Dr. Todd Ely, and I'm the Principal Investigator and Project Manager for the Deep Space Atomic Clock.
And I'm Dr. Jill Swibbert. I am the Deputy Principal Investigator.
We've been working on this project for over 7 years, and we're really excited to be here today to tell you all about it. The Deep Space Atomic Clock will be the first ever ion-based space atomic clock to fly, and it will also revolutionize the way in which we'll navigate through deep space. We expect this to be a key part of sending humans to Mars and be a key component to future GPS-like navigation systems at the moon and Mars and other planets and moons.
So let's start with a short animation that will describe this mission's technology to you.
How do we navigate through space? Currently, spacecraft flying beyond Earth don't have a GPS to find their way through space. Navigators on Earth send a signal to the spacecraft, which receives it and sends it back. Extremely precise clocks on the ground, called atomic clocks, measure how long it takes the signal to make this two-way journey. The amount of time tells them how far away the spacecraft is and how fast it's going. The farther out in space the spacecraft is, the longer it takes to receive and send the signal. But what if humans are sent to another planet, like Mars? A two-way system that sends a signal from Earth to a spacecraft, back to Earth, and then to the spacecraft again, would take an average of 40 minutes. Imagine if the GPS on your phone took 40 minutes to calculate your position. You might miss your turn, or be several exits down the highway before it caught up with you. If humans travel to the red planet, it would be better if the system was one-way, allowing the explorers to immediately determine their current position, rather than waiting for that information to come back from Earth. NASA is testing new technology that would allow future explorers to do just that. The Deep Space Atomic Clock is the first demonstration of an atomic clock that can be used for navigation in deep space. It will allow a spacecraft to calculate its own trajectory instead of depending on Earth. If a spacecraft had one of these clocks on board, it could receive a signal from one of those big antennas on Earth and quickly measure its speed and position. The Deep Space Atomic Clock could one day let astronauts navigate safely and accurately to Mars and beyond. This technology demonstration is the first step in making one-way space navigation a reality.
So Todd and I are deep space navigators, and our jobs are seriously just as cool as you might imagine. We get to steer spacecraft. We are pilots of these deep space spacecraft. From the moment they separate from their launch vehicle all the way to when they reach their destination in deep space. We're sending spacecraft to places like Mars, Jupiter, Saturn, and these destinations are extremely far away from where they started. To put our jobs in context for you, it's like us standing here in this room at Kennedy Space Center, and we shoot an arrow. And with that arrow, we hit a target that's about the size of a quarter that's balancing on top of the Seattle Space Needle. So it's quite a journey that it has to take. But we do get the opportunity to correct that journey, that trajectory, a few times along its way. But in order to do that, first we need to know where a spacecraft is. And tracking a spacecraft as it travels through space is fundamentally a problem of measuring time, as you saw in that video just there. These spacecraft are really far away. I can't pull out a ruler and measure the distance from me to the spacecraft, right? But I can measure how long it takes for the spacecraft to echo back a radio signal that we sent from the Earth. And the longer it takes for me to hear that echo back here, the further away my spacecraft was. So to navigate safely, we measure that echo, that signal return time, very, very accurately, down to better than 1/billionth of a second. But in order to measure it that accurately, we need to use those atomic clocks in the Deep Space Network here on the Earth that were, as you saw in the video, quite large. They're about the size of a refrigerator. Now, because of this limitation, we can't really put that on a spacecraft and send it into deep space easily. Because of this, every single spacecraft that's out there exploring deep space is being navigated by people back here on the Earth, people like myself and Todd. But the Deep Space Atomic Clock is actually here to change that, because we have taken the performance of those refrigerators and we've shrunk it down to something that's about the size of a toaster oven here. And Todd's going to tell you more about how the clock operates.
So you may not realize it, but most everybody here today use a GPS, or excuse me, an atomic clock. And that's because atomic clocks are part of every GPS satellite in orbit. And we use those GPS satellites in our GPS-enabled apps, Maps, Google Maps, Apple Maps, so forth, to get here. And then you may then ask, so if GPS atomic clocks can work for that, why can't we use those for deep space navigation? It's because the deep space atomic clock is about 50 times more stable than those GPS clocks flying today. It is exquisitely precise. In fact, the deep space atomic clock, we expect to lose or gain less than 0.3 of a nanosecond over the course of a day. And that translates into something like a second over 10 million years. And then you may ask, well, why do we need that level of precision? It's because light travels fast, very fast. So if you can imagine a light signal or a radio signal which travels at the speed of light is traveling from Earth to the moon, it takes a little over a second. So we really need to get our timing right. If you can imagine sending that same signal from Earth to Mars to figure out the distance of that spacecraft, if we miss that timing by a second, we've effectively missed hitting Mars by the same distance the moon is from the Earth. So how does the Deep Space Atomic Clock do that? It uses mercury ions like a tuning fork. And with that capability, we produce a very stable output signal that we measure time very precisely. And with this capability, we can measure that same distance from Earth to Mars to within a meter using the Deep Space Atomic Clock. And we expect that clock to change the paradigm, that two-way tracking paradigm that Jill described, into one in which is one way.
So this clock technology means that we don't need to navigate with radio signals that are sent from the Earth to the spacecraft and then back again. Now we can use signals that are sent from the spacecraft directly to the Earth, or vice versa, from the Earth to the spacecraft. Now firstly, this allows us to use our existing deep space network more efficiently and more flexibly than we can today. The Deep Space Network is limited in how many spacecraft it can talk to in two-way mode at once. To one. It can only talk to one spacecraft at a time in that way. Now there's a lot of spacecraft that are flying through deep space, and right now, to get two-way tracking, they're all fighting for time on those antennas. They're time-sharing the ground antennas. The atomic clock will change that by allowing the DSN to track more spacecraft simultaneously. That means more navigation data, better navigation solutions. Now, if we can cut to our image and show it on the TV for a second here, it's just a teaser of some of the other cool applications that we can use this clock for. Primarily, they'll help us on our journey to get humans to the moon and Mars and perhaps beyond one day. If we are broadcasting a radio signal from the Earth out into space, what's stopping that spacecraft from collecting that radio signal on board and doing its own navigation? Why does it need to be navigated by humans back on the Earth here? We call this autonomous onboard navigation, in which the spacecraft will collect the signal and its onboard computer would compute the trajectory, predict where it's going, and compute any trajectory correction maneuvers that it would need to execute. In other words, where to point, when to fire the thrusters, for how long to fire the thrusters, when to do this action in order to get back on its trajectory to hit its target in deep space. Onboard autonomous navigation, you can think of like a self-driving spacecraft. And it's one of the top technologies that we need to send humans to places like Mars. You can imagine when we have a human crew on board, we want to navigate the ship in real time, not wait for directions to be sent from the Earth to the spacecraft. This lets our human crew land on their landing site on Mars with less uncertainty in their path, so it's a safer and more robust way to navigate those humans. Now, when we inevitably send humans to the moon, onto Mars, or beyond, it would be really nice if they had a way to find their way around the way that we all found KSC's press site today. Well, with this Deep Space Atomic Clock, we can now build GPS-like navigation systems at other planets and moons. So imagine if the astronauts on the moon had GPS that they could use to find their way around, or an astronaut on Mars. Can you see an astronaut on Mars with Olympus Mons rising in the background, and she's looking down at her Google Maps Mars edition to see where she is and to plan a course to get where she needs to go? You can understand this technology is really critical if we're going to support a continued human presence on any of these locations. And then finally, if you let me think really far, far in the future, one day we might be